Swayam Prabha. Digital India. Educated India.
The cell membrane has a voltage across it, a potential difference across the membrane with the interior being negative. In the very first lecture in this series, we have seen that if we put electrodes on either sides of the cell membrane, we will be able to record a potential difference as high as 70 to 90 millivolts, especially in excitable cells. Whereas in non-excitable cells, the potential difference can be much less, about 30 to 40 millivolts. Nevertheless, the interior in the resting state in excitable as well as non-excitable cells will be negative with respect to the exterior. And our question for this session is to understand how this potential difference comes about. What is the cause for this membrane voltage at rest? We will start the discussion from where we left it in the earlier session. In the previous session, we were considering the Donen effect. Cells lay down proteins and phosphates within themselves. These happen to be anions, impermeant anions at that, because the cell membrane does not have transporters for these, and therefore they cannot cross the cell membrane. Presence of impermeant ions in a compartment will induce an effect called a Donen effect, wherein there will be water entry into that compartment, consequent cell swelling and lysis. So this effect would be deleterious to a cell, and cells have evolved strategies to counter the Donen effect. The animal cells handle the Donen effect of the impermeant anions within the cell by maintaining sodium as an impermeant ion outside the cell. It does that by pumping sodium out through the sodium-potassium pump. While these cations are maintained on the outside, the cell does need cations, and the same pump recruits potassium ions from the extracellular fluid and pumps it into the cell. Now, while the impermeant anions are really impermeant, we know that sodium does move into the cell through various transporters. We have seen a whole array of secondary active transporters, which are sodium co or counter transporters. It does enter the cell, but whatever comes in is thrown out by the sodium potassium pump, so that sodium is effectively impermeant. Now, one word of caution about Donen effect. It is not bad in every situation in the body. In the cell, the Donen effect has to be handled by the cell, has to be countered by the cell. But in the vascular compartment, the Donen effect of plasma proteins is a desirable effect. We will consider that later on. Now, we can understand why the intra and extracellular compartments have different ion compositions. The major electrolyte in the extracellular compartment is sodium chloride, and in the intracellular compartment we have potassium as the major cation and a set of impermeant anions, which are the proteins and organic phosphates that the cell synthesizes. Given this ion composition in the fluids, we now have to see why there is a potential difference across the cell membrane. The exterior is positive and the interior is negative, and the magnitude of the field is about 80 millivolts in excitable cells. When we put electrodes in these compartments. By virtue of the technique, the external compartment is earthed, that's the reference electrode. However, the field per se will not change as the inside will become that much more negative, and that is what we are measuring as minus 80 millivolts. And the question we are trying to answer is, why is there an internal negativity? Before answering this question, let us understand how membrane potential is actually measured. I have come across some unconventional methods of measurement of membrane potential, like putting a fluorescent dye within the cell, and the dye will fluoresce with different colors at different voltages. However, the conventional and the traditional method of measuring membrane potentials is to actually place an electrode within the cell and measure the potential difference across that intracellular electrode and an external reference electrode. The intracellular electrodes themselves can be of two types, what are called sharp electrodes. These are very thin electrodes with a very high resistance. We will not talk about it any further. And the second type of intracellular electrode technology is what is called the patch clamp technology. Now, this technology was invented by two German membrane biophysicists, Professor Erwin Neher and Professor Sackmann. Professors Neher and Sackmann, using this technology, recorded currents across a single channel, a real feat, and for that invention they were honored with a Nobel Prize in 1991. I was fortunate to learn about the fundamentals of the patch clamp technology from Professor Robert Chow, then at the University of Edinburgh and now at the University of Southern California, Los Angeles. Professor Robert Chow did his postdoctoral fellowship with Professor Neher himself. In this technology, an intracellular electrode is placed on a cell under microscopic guidance. The microscope itself is an inverted microscope. It's preferred because in an inverted microscope, the objective is below the stage. In an ordinary light microscope, the objective is on top and it has to be very close to the object. So you do not get a good working distance. Here, since the objective is below the stage and the light source is above, there's a good working distance to bring and place an electrode on a cell. There will be an opening on the stage or a transparent area on which you place a dish with cells in it. The cells are bathed in an extracellular fluid, and the extracellular fluid composition is similar to that of plasma or tissue fluid in which cells would normally reside. This fluid is prepared in the laboratory to resemble extracellular fluid. Sodium concentration would be about 140 millimolar, potassium about 5 millimolar. Extracellular potassium is very important and is maintained within a very narrow range of 3 to 5 millimoles per liter. Chloride in plasma is about 110 millimoles per liter, and the other anion in plasma or extracellular fluid would be bicarbonate at about 22 to 25 millimoles per liter. But for technical reasons, bicarbonate is kept out of the solution and in fact replaced with chloride, and another buffer is used to keep the pH at 7.4. That is the extracellular solution which is there in the bath, and there will be a bath electrode, the external electrode, which will connect to the voltage measuring device. The internal electrode has to be fabricated. It's called a pipette, a patch pipette, and it is made from a glass capillary of very fine dimensions. This glass capillary will have to be heated with a coil. This is a coil made of nichrome wire usually, and the glass capillary is placed within that. It is fixed on top and there are weights attached to the bottom. When the nichrome wire is heated, the center of the glass capillary will get heated and thin out, and the weight will pull it down, breaking it into two pipettes, patch pipettes. The tip diameter is of the order of 2 microns. Generally, the tip diameter is not spoken about as microns. The tip dimensions are spoken of as resistances. Patch pipettes have 2 to 5 mega ohm resistances, and at that resistance they will have a tip diameter of, let us say, 2 microns. What I am trying to say is that tip diameter is much less than even a very small cell. Even an RBC would be 7 microns in diameter, and the dimensions of the tip of this patch pipette is smaller than the smallest cell. This patch pipette will now have to be filled with an intercellular solution. This is the composition of the intercellular solution: potassium at 130 millimolar. Now, rather than use proteins or phosphates, we use other impermeant anions. The intercellular anion can be gluconate. This is an impermeant anion. So, your intercellular solution is made with potassium gluconate, or sometimes potassium methane sulfonate. You could choose the impermeant anion you want to use. This intercellular solution will be taken in a beaker, and the patch pipette is inserted into it. The solution rises through the tip of the patch pipette by capillary action. That is the best way to fill that part of the patch pipette, and the rest of the pipette is filled with the same solution from above. Now, this filled patch pipette is then threaded on to a silver wire, which is going to function as the electrode connecting the intercellular fluid to the amplifier, which will record the voltage. Now, the filled pipette is threaded onto the silver wire into this pipette holder. There's an O-ring here, a rubber ring, which makes an airtight seal there. There's a side port in this opening here, and this side port is in communication with the interior of the pipette, so that if you apply any pressure in the side port, it reflects in the pipette. You could either give a suction pressure or you could give a positive pressure. And I'm told that this side port was crucial to Nernst invention. This pipette holder assembly is then connected to what's called a preamplifier or head stage, in which exists the first level operational amplifier, which will measure the voltage. This whole assembly is then brought near the cell with the help of a micromanipulator, which can move in submicron dimensions under microscopic guidance. The reference electrode in the bath is then connected to the preamplifier. The preamplifier is then connected to the patch clamp amplifier, as it is called, which then goes to a computer, and the voltages are recorded by the computer. The pipette assembly is then lowered to touch the cell with the help of the micromanipulator. Now, let us zoom in and see what it would look like through a microscope, still a cartoon. There is a cell, and let us say this is the filled patch pipette which has touched the cell. There is the intercellular solution here. Now, we know that the patch pipette is a side tube, and there would be a plastic tubing connected to that, with which we can give mouth suction. Now, once in this position, some suction is given so that a little bit of the cell membrane is sucked into the patch pipette. Now, once this small omega goes into the patch pipette, what is called a giga seal is achieved. By giga seal, what is meant is that the resistance between the cell membrane here and the tip of the pipette is of the order of giga ohms. What it essentially means is that there's an electrically tight junction between the pipette tip and the cell membrane. So there can be no short circuiting of currents through the pipette tip. All the current has to go across the cell. After this configuration, there are 4 different configurations of patch clamp possible. I'm not going to discuss all of them. We are only going to look at what is called the whole cell mode of patch clamp. Now after this, after attaining a giga seal between the tip of the patch pipette and the cell membrane, a sharper pulse of suction is given so as to break this membrane here. The membrane actually goes and attaches itself to the sides, inner sides of the pipette, and instantaneously fluid from the pipette fills the cell. The cell volume per se is of the order of picoliters, and the pipette volume would be more than microliters, at least few hundreds of microliters. So essentially all of the cell content is replaced with the intracellular solution that we designed and made in the laboratory. So this is how we will be able to change intracellular concentrations of ions to our liking to do experiments. We will see some of these experiments as we go. Now in this mode, what's called the whole cell mode, so that is the silver wire, which is the intracellular electrode, and we already saw we had a bath electrode. The voltage across these 2 electrodes is measured by the patch clamp amplifier, and what we would record is a negative potential because the active electrode is inside the cell and the bath electrode is actually grounded. Our question for the session is, how does this internal negativity come about? These are the concentrations of the solutions we prepared for the experiment. Extracellular fluid is sodium chloride predominantly, and intracellular fluid would be potassium gluconate. With these solutions, we would record a negative potential. I've stated it as -70 there, that is fine. A steady negative potential would be recorded, and that is what we call the resting membrane potential. That's the question for the session. Now the answer to this question was realized as early as 1902 by Julius Bernstein. Very intuitively, because none of the armamentarium we have today was available then. Not even knowledge. Channels were not yet tangible concepts at that time. In spite of that, Julius Bernstein had rightly figured out what the cause of the resting membrane potential is. Rather than state it in one simple sentence, I'm going to attempt to present to you 2 popular answers that I get when I ask this question. Why is there a negative membrane potential within cells? And I'm going to argue on the lines of those answers. So when I ask this question in a regular class, the most common answer that I get is, it is because there are impermeant anions within the cell, that is why the interior of the cell is negative. Very deceptively simple logic. But then, it is a valid hypothesis and we have to test it out. So let us state that our hypothesis is that the internal negativity within the cell is due to the presence of impermeant anions within the cell. How do we test this hypothesis? Of course, by removing that impermeant anion and replacing it with a permeant anion. So if we take gluconate out and replace it with chloride itself, the cell membrane has channels for chloride. Now, if the large anions within the cell are replaced with chloride, How do we do that replacement? Of course, you can't change gluconate for chloride while you have patched a cell. It is possible, but technically very demanding. What we would do is, we would prepare another intracellular solution with chloride as the main anion and fill another pipette and patch another cell. And if we do that, we would still record the same negative resting membrane potential. Therefore, the internal negativity is not due to the impermeant nature or the nature of the intracellular anions being very large anions. That is not the reason for the internal negativity, because even if you provide small anions for which the membrane has transporters like chloride, even then the internal negativity exists. So, it is not as if that the internal negativity is due to the presence of large impermeant anions within the cell. So, it looks like it is not an anion excess, but rather a cation deficit. So, that answer, I argue with the students, is not a correct answer. The next popular answer that I get is that the internal negativity is due to the stoichiometry of the sodium-potassium pump. That is, the pump transports 3 sodium ions out, but only takes in 2 potassium ions for every turn of the pump. So, there is a net loss of cations with every turn of the pump, and therefore, the inside is negative. So, this is another answer I get, and if that was a hypothesis, how will we test it? By blocking the sodium-potassium pump. If that pump or the stoichiometry of that pump was the reason for the internal negativity, then by blocking it, we can block it with the use of pump blockers like Wobane that's used in the research setting. There is also a therapeutically used blocker of the sodium-potassium pump, digoxin. Now, if we put Wobane at very low concentrations in the extracellular fluid and block the sodium-potassium pump, if that stoichiometry of the pump or that pump transporting 3 cations out while taking in only 2 was the cause for that internal negativity, then we expect the internal negativity to be abolished when the pump is blocked. What would we actually see? When we add Wobane, the negativity reduces, but ever so slightly. Much of the potential still remains. So, my argument is that the sodium-potassium pump is not the immediate cause of the resting membrane potential. We will come back to the issue of sodium-potassium pump later during the lecture, but since Wobane blockade does not, within a very short time frame, depolarize the cell or neutralize the polarity, we understand that that potential difference is not due to the electrogenicity of the sodium-potassium pump. So, that second popular answer that I get from students also does not seem to be correct. What then? Now, we know that there are channels for all these ions on the cell membrane. What if this membrane potential is a result of diffusion of these ions through their channels? Is it a diffusion potential? Something that could be predicted by the Nernst equation? A diffusion potential or an equilibrium potential? Is that what it is? What do we mean by that? Let us ensure that we know the direction of the current if those channels are open. Sodium would move inward through sodium channels along the concentration gradient, and sodium being a positive ion, the current would be in the same direction as the cation, and that would be an invert current. And remember, Dr. Vinay had told you that invert currents in the patch clamp convention are designated as negative currents. Just remember them as invert currents now. Potassium would diffuse out of the cell if its channels were open, and potassium would therefore be an outward current. Potassium is also a cation. Chloride would diffuse inward along its concentration gradient if chloride channels were open, but since chloride is an anion, the direction of current due to chloride movement would be in the opposite direction. This is again convention. Now, if the membrane was permeable to all these ions at rest, or if all these channels were open at rest, then there would be no potential difference across the membrane. It would be a membrane with multiple holes in it, and therefore there would not be two compartments even. There is a very permeable membrane. So, these two compartments essentially become one and the same, and there would be no potential difference across the membrane. A potential difference would arise only if the membrane was selectively permeable to one or other ion, and therefore would reach the equilibrium potential for that ion. So, that is our question. Is the negative internal potential some kind of a diffusion potential due to the membrane being selective for one or other ion? Now, let us consider each possibility. Let us suppose the membrane at rest is selective for sodium ion. By that I mean only sodium channels are open in that membrane. Theoretically, if we could think of a time 0 when the sodium channel suddenly opened, then there would be an inward current, but sodium influx cannot go on forever because it is not accompanied by an anion. Very soon, by soon I mean in the order of milliseconds, the inside of the cell will become positive, and when the positivity is of sufficient magnitude to balance the concentration gradient, then sodium influx would cease. So, that potential, we already know it is a positive potential, at which sodium influx would cease even if its channels were open, because that potential balances the concentration gradient. That potential is called the equilibrium potential for sodium. It is very obvious that the equilibrium potential for sodium, or the internal potential at which sodium influx will cease, is positive, is very obvious. We can even quantitate what this potential would be. This potential can be predicted by the Nernst equation. If you know the concentrations on either sides, the potential that builds up would be exactly equal and opposite to the energy of the concentration gradient. So, you can predict what the equilibrium potential would be if you know the concentrations of the ion on either sides. That is what the Nernst equation does. It tells you that the equilibrium potential for sodium across a membrane which has two different concentrations of sodium outside and sodium inside is 60 log sodium outside by sodium inside. Now, this 60 is 2.303 into RT by ZF, R being the gas constant, T absolute temperature, Z is the valence of the ion, and F is the Faraday's constant. All that reduces to this constant 60. Okay. Now, sodium outside is 140 and sodium inside, I am just putting it as 14 for ease. Equilibrium potential for sodium in this situation would be 60 log 10, which would be 60 millivolts or plus 60 millivolts. We already knew it is a positive, it has to be a positive potential. We now know the magnitude of that potential as well. Anyway, our question now is, why is there a negative potential within the cell? It is very obvious it is not the sodium equilibrium potential, or we can state that the cell membrane does not have open sodium channels at rest. Alright, the other two possibilities are that the resting membrane potential is a potassium diffusion potential or a chloride diffusion potential. Let us consider chloride first. we are now considering the option that the resting membrane potential is a chloride equilibrium potential, just like we considered for the sodium channel. If there was a time 0 when the chloride channel suddenly opened up, there would be chloride influx, but very soon the inside of the cell will become negative, and when that negativity is sufficient to balance the concentration gradient, chloride influx would cease. So that negative potential would be the equilibrium potential for chloride, and that can be calculated with the help of the Nernst equation. So given these concentrations of chloride, chloride equilibrium potential would be 60 log 145 by 4. You could either choose to invert the ratio because chloride is a negative ion, or after you get the result, you could put a minus there because chloride is a negative ion. So the magnitude of the internal potential at which chloride influx would cease, or the chloride equilibrium potential given these concentrations of chloride, would be minus 96 millivolts, which is looking very much like our resting membrane potential. The magnitude is similar. We were talking about minus 80 to minus 90 millivolts. So the question is the resting membrane potential a chloride equilibrium potential? Now I am going to qualify my statement. Is the resting membrane potential in a nerve cell a chloride equilibrium potential? How can we test this? Well, if the membrane was permeable to chloride at rest, and if the resting membrane potential was indeed a chloride equilibrium potential, then if you alter the concentrations of chloride on either side of the membrane, then the potential would change as predicted by the Nernst equation. So what we can do is use an intracellular solution rich in chloride, and now if we predict the equilibrium potential for chloride, given that chloride concentrations are equal on either side, we would see that there would be no potential difference across the membrane because there is no concentration gradient even though that channel is open, and mathematically 60 log 1 would be 0. This is what the Nernst equation would predict, but in a nerve cell, even when you have kept chloride concentration at 145 internally, you would see that the resting membrane potential still exists. Actually, we have done this experiment in an earlier context where we replaced internal gluconate with chloride. So even if you had equal chloride concentrations, if you expected that the membrane potential was a chloride equilibrium potential, then when you have symmetrical chloride, the membrane potential should not be there. The membrane should depolarize completely, but the membrane doesn't and is still at a negative potential. So at least in a nerve cell, the resting membrane potential is not a chloride equilibrium potential. That leaves us only with one option now, that the membrane is at the potassium equilibrium potential. We will do the same considerations for potassium. Let us assume that the resting membrane is permeable only to potassium. Our hypothesis now is that the resting membrane potential of the cell is a potassium equilibrium potential. Again, we are making the implicit assumption that the resting potential of cell is due to the fact that the membrane is permeable only to potassium at rest, or that it has only potassium channels that are open. Though there are other types of channels, they are all closed. That is the implicit assumption we make when we say that the resting membrane potential of a nerve cell is the potassium equilibrium potential. So let's see what the potassium equilibrium potential would be given those concentrations of potassium. So if the channel is open and potassium leaves the cell, it can't go on forever, because very soon an internal negativity would build up, and the magnitude of that negativity can be calculated with the Nernst equation. It tells us that the internal potential at which potassium efflux would cease and potassium would come to an equilibrium state is minus 85 millivolts. That is again very much like the potential we record across the membrane. So it is likely that the resting membrane potential is indeed the potassium equilibrium potential. We can test this along the same lines as chloride. We can alter potassium concentrations. It's easier to alter it outside. Even while the cell is being patched, you can change the external potassium concentration by adding more potassium to the bath fluid. So let us do that now. Let us change external potassium to say 65 millimoles per liter. And now the equilibrium potential for potassium as predicted by the Nernst equation would be minus 18 millivolts. Now what happens to our recorded potential when we have increased extracellular potassium? Yes, it does reduce. In your recording, you would see that when you had 5 millimolar potassium outside, you would have recorded a certain negative potential. But if you increased potassium concentration in the extracellular fluid, the membrane would depolarize and would reach a new potential, which is the potassium equilibrium potential for that set of concentrations of potassium. So it is becoming obvious that the resting membrane potential is because the membrane is permeable only to potassium at rest. We can extend the experiment like for chloride. We can increase potassium outside to 130, make the potassium concentrations equal on either side, and then we expect the potential difference to neutralize or the membrane to completely depolarize. That's indeed what will happen. We will not record a potential difference if we had equal potassium on either side of the cell membrane. So while you're recording, if you increase external potassium to 130, you would notice that within a frame of milliseconds, the cell membrane would completely depolarize. There's no potential difference across the cell membrane. We have now arrived at an answer to the question that we started with. Why is the membrane negative at rest? Why is there a negative membrane potential? It is because the membrane at rest is permeable only to potassium and therefore has reached the potassium equilibrium potential. When you change potassium gradients, the membrane potential that you record with the patch clamp technique changes as predicted by the Nernst equation, and that confirms that the resting membrane potential is a potassium equilibrium potential. Another way to test the hypothesis is you can block the potassium channel with blockers like tetraethylammonium chloride, and then again the membrane should completely depolarize. That's what you will see. There won't be any potential difference across the cell. So even if you use tetraethylammonium, the cell will depolarize completely. All right. We've seen this table of channels earlier. Where in this table should we look for the potassium channels that are open at rest and contribute to the resting membrane potential? Very obvious. This is the column with constitutive channels, that is, channels which are open all the time, open at the resting membrane potential. That's where we have these potassium channels listed, leak potassium channels or inward rectifiers. The KATP channel is also a class of inward rectifier. The others are all closed at rest. These are voltage gated potassium channels. It is this class of potassium channels that were open at rest and contributed to the membrane potential, resting membrane potential. Now, you would wonder about these other ion channels that are listed here, which are also open at resting membrane potential. Now, notice that all these are found only in the epithelial tissue, in the renal epithelium and the intestinal epithelium, located there for absorption of these ions. They are not present in the excitable cells of your body and the other cell types other than epithelial cells. So, for all practical purposes, you could think that the channels that are open in any cell for that matter at rest are potassium channels of this type, and therefore the membrane is at the potassium equilibrium potential. That is the resting membrane potential. So, it's easy to summarize now. The membrane at rest is at the potassium equilibrium potential. There's one exception, the skeletal muscle cell. I learned this the hard way, and therefore I want to make this statement. The skeletal muscle resting membrane potential is contributed to by both potassium and chloride. Potassium and chloride channels are open in a resting skeletal muscle cell, and unless you block both, the skeletal muscle cell will not completely depolarize in an experimental situation. I hope I've made my understanding of the resting membrane potential clear. Thank you for watching this NPTEL lecture.